Hi, welcome back to our Honors Geometry playlist. Sorry I'm not there today. Hoping to be back tomorrow. I would ask you to just pause the video and fill out these definitions, and then unpause when you're ready to move on. So we're talking about perpendicular bisectors, angle bisectors. We've been working a lot with bisectors in our triangle congruence theorems. And when I have bisectors in a triangle, whether they're angle or perpendicular bisectors, we're going to find out that my bisectors all intersect at one point. And we call them different things based on what the bisector is. So my perpendicular bisectors, they would all meet at a single point that I would call the circumcenter. So my perpendicular bisectors of a triangle all meet at what I call the circumcenter rather. And the angle bisectors of a triangle would meet at what we call the incenter. And those points where two or more lines meet, the incenter and circumcenter, I would call those points of concurrency. So perpendicular bisectors, if I have a perpendicular bisector of a segment, so if I have a perpendicular bisector of segment BC, if I were to bisect that at a right angle, then that point, any point on that perpendicular bisector would be equidistant from the endpoints of the segment. And if we think about this like a Pythagorean theorem problem, it makes a little bit more sense. So let's consider two right triangles. I bisect that segment, BC, so I cut it into two equal parts. The left side is 3 units long and the right side is 3 units long. Maybe the height is 4 units, so maybe it's 4 units tall. Then let's focus on just the right side of that picture. Well, if I had 3 and 4 as the lengths of my triangle, if it's a right triangle, I know that I could find the hypotenuse using my Pythagorean theorem, and it would be a 3, 4, 5. And similarly, if I had a right triangle that was 3, 4, 5 on the other side, I know that the hypotenuse must be 5 units long. So I've got 3, 4, 5, and 3, 4, 5, which means that AC has to be congruent to AB, or AB is congruent to AC. And it works in reverse as well. It says that the converse of the perpendicular bisector theorem, the opposite direction, says that if some point is equidistant from the endpoints of a segment, so maybe this is 6 units long, if A is equidistant from the endpoints of the segment, then it must be on the perpendicular bisector. So let's look at a few examples. Here are some perpendicular bisectors. And I know two things. I know that if this is a perpendicular bisector of segment RL, I know that RM should be congruent to ML. I know that that's a right angle if it's a perpendicular bisector. And I also know that KR should be congruent to KL. I know that this point K should be equidistant from the endpoints of the segment. So KR and KL should be equal. They should both be 4.2 units long. In the same way, we can solve letter B. If EF and ED are equidistant or congruent if E is equidistant from the endpoints of that segment, then I know it must be bisected. This must be a perpendicular bisector problem, which means that 5x minus 17 has to be equal to 3x plus 1. And then finally, same idea here, I've got a perpendicular bisector. It's perpendicular. I'm seeing some congruence marks that say it's bisected. And I know that if I have a perpendicular bisector, then the distance from K to either endpoint would have to be the same. So 3x would have to be the same length as x plus 10. And now if I wanted to show this geometrically, right, if I wanted to prove that like we did before, well, check it out. I've got a side by my reflexive property. I've got a right angle and I've got a side. I have side angle side congruence. So I know that those corresponding parts must be equal. Same thing here. I've got a side. I've got a right angle. And now this one I don't have side angle side, but I do have hypotenuse leg. So side angle side, I would need my angle to be up there, but I don't have that. What I do have is hypotenuse of 13, and this reflexive property side, e.g. the leg. So I do have hypotenuse leg there. And over here, I have a side angle side congruence if I use my reflexive property. So you could also prove that these are congruent by, side angle side or hypotenuse leg, and use that to say that the corresponding parts must be equal or congruent as well. So x would have to be 5, or x would have to be 9 here, and you could plug that back in and get 28 and 28 and 15 and 15. So you've got some options there. Now the circumcenter, that's where my perpendicular bisectors of a triangle meet. And that circumcenter is equidistant from the vertices of the triangle. So let's look at one example here. I've got a circumcenter P. And that circumcenter is made by finding the perpendicular bisectors of all of these sides. Well, what does that tell me? That tells me that AS and SC or CS must be congruent because it was bisected. I know that AR and BR should be congruent because that side was bisected. And I know that BT and TC should be equal because that segment was bisected. So I know that BR should be congruent to AR. I know that CS should be congruent to AS. And I know that BP, that's an interesting one. That's an interesting one because what is BP? That's the distance from the circumcenter to the vertex. We have a theorem here that says that the circumcenter is equidistant to all the vertices. So if BP or PB is the distance from the circumcenter to one vertex, that would be the same length to the other vertex A or to the third vertex C. So you could say that that is congruent to AP, or you could say it's congruent to CP. So all those segments that go from the vertex to the circumcenter would all have to be equal. So if this is 7, then that would have to be 7, and this would have to be 7 as well. And we can talk about why that is later on, but for today I just want you to know that that theorem exists. Let me go back. I'm going to color code that again, so it would be AP or CP. Okay, so that's it for perpendicular bisectors. Our angle bisectors, if a point's on the angle bisector, then it is equidistant from the sides. So if I have a triangle here, I'm going to try to make that look not special in any way. If I were to bisect an angle, I'll try to make it look kind of close. And I'll bisect this angle. And they should all cross at a single point. If I bisect all my angles, then it's equidistant to the sides. So the distance from this incenter to one side would be equal to the distance from that incenter to the other side or to the third side. So the distance between the incenter and the sides would have to be the same as well. And it works in the opposite direction with the converse as well. If a point is equidistant from all the sides of a triangle, then it must be on the angle bisector. So let's look at a few problems here. I've got some angle bisectors. So this angle bisector here, YL, is cutting the angle JYF, angle JIF for all you peanut butter fans, or FYJ. It's being bisected. So the left half, 58, must be congruent to the right half of 58. And I also know that the distance from this angle bisector to either side would have to be congruent. Now they wanted angle LYF, which ended up being 58 degrees. That was the other half of that angle. Let's look at example B. IU is the distance they want right here. Notice that they were given an angle that was cut into two equal parts, so that is an angle bisector, which means that the distance from any point to one side of the angle must be congruent to the distance from that same point to the other side. So 7x must be equal to 2x plus 5, or x would have to be equal to 1. So this would be 7, or IU would be 7. Alright, let's take a look at this last example here for this video, and then I'll do a separate video so that it uploads a little bit nicer for you. Angle MYW, that should be angle MYW, which is right here. I want to know, what does that angle measure? And notice that the distance from the point M to either side of the angle it's equidistant to either side, right? Which means that that has got to be on the angle bisector. So that means that 2x plus 5 should definitely be equal to 4x minus 1. So it's 2x is 6, or x is 3. So this should be 11 degrees if I plug that back in. Substitute that back into the original expression. Okay. I lied. I want to do one more problem before we head off to the graphing video. So on this problem, my incenter theorem, just as a reminder that the incenter is equidistant from the sides. So check this out. I've got an incenter. So there's two things I need to note. That is an angle bisector. So number one, that's an angle bisector. And number two, that is equidistant to all three sides. check it out. I've got my angle bisectors here, so all these angles are bisected. All these angles are cut in half. And if all these angles are cut in half, the left half, or the top half, must be equal to the right half or the bottom half. So I don't know what these two angles are here at Q, but maybe I could put like an X and an X. That's not a good idea. I could put a Y and a Y. I don't want to reuse a variable. At angle R, in the bottom right corner, I've got 40 degrees. Well, if that was bisected, that means this must be 40 degrees as well. And then up top, I know that if this was bisected, that these two angles must be equal. So 3x plus 2 must be equal to 4x minus 9. And then I could solve for my missing angles ARU and QPK. Now let's talk about the segment lengths. They said that AT was 8. So AT was 8. And we found earlier that if it was an incenter, it must be on the angle bisector, so point A is on the angle bisectors, and it must be equidistant to all three sides. So A to the side over there must be 8. Well, I've got some other segments here that are from point A to the sides of the triangle. And if that really is an incenter, then those must be equidistant. Those must be congruent segments. So AU should be 8 units long as well. Alright, that's it for the non-graphing portion. Check out the graphing video, and I will see you tomorrow.